So it's displayed in the laptop. So this technology is very, very, it was picked up in 2000. It's called smart dust. I don't know whether how many of you heard. The name is given called smart dust. So you saw the dust particles, right? The dust particles, imagine the dust particle is it has got a little memory, it has got a processor, it has a communication, and it's a dust. You throw the dust particles, it organizes itself, and then it basically measures things and communicates. So there's a lot of technology used, and there's a lot of applications, both commercial and military. So I'm just checking what else. There are so many, but not of interest to you probably. That's why I'm not showing this. Okay, guys. So let's see here. So how do you test? Something is AI, right? So things like, what is the real way to know whether something, remember I keep saying earlier in 90s we are programming. Now we don't program, we let the agent learn by itself. So what is the best way to test it? Is like if the computer can beat a human or do as good as a human. Okay? So there's a lot of work going on in here, and you guys have done Q learning, right? Now this is a deep Q network. I'll show you deep Q network. I don't know whether you guys have played any of these games, Breakout or Space Invaders. You played? Okay, so then you are familiar. So we were trying to look at it and see whether a computer can play and do better, can get a much better score. Okay? So you can see here, you see this bar moving left and right, and it can also go up and down. So that's your action. Okay? And then input is the image. Just like our eyes, you're seeing that. So the input is the image. So you're feeding so many images. Okay? And the output is basically moving this bar left and right. Okay? So this work, some part of it is done with collaboration with IIT Kanpur. All right? So now, if you look at this, so this is before training. It does really bad job. Because if the ball doesn't come back, it fails, right? So now this is a well-known, celebrated, what we call stochastic gradient descent. This is what all these Google and everybody uses, mostly stochastic gradient descent. You see that in the top there is this score. It takes a long time for the score to improve. Look at that. So you are not teaching that system what to do or how to do it. Okay? So unlucky run. So what we did, we developed our own method. Okay? And we tried it with using our own method. You see how quickly it learns. And look at the reward. So that's the beauty of the real time. That is the beauty. You see? So we are not teaching the system how to do it. We only tell them what to do. And the whole network is able to learn, understand, and make decisions so that the goal is to maximize the reward. In this case, you're maximizing it because it's basically the score that you are trying to maximize. You see? So this is where it's going. Okay, so there are also other programs. We also have Space Invaders. So we have done, you know, quite a bit. You remember the hybrid stuff? The hybrid where we have combined some iterations, and that's the one. And there are so many videos. Those are all videos. I can sit here and play for 3-4 hours, you know, all of them. There are so many. We implemented so many hardware videos, mostly hardware, and this is basically the one, you know, you can run them, you know. Oops. These are different methods. They are completely different methods that how each of these methods work. See, the hybrid is the one that is a combination of iterations and once a sampling instant. So so this is how we evaluate something is really going well. So what is that, you know, I don't have that stuff. It's actually a Q-learning, deep Q-learning. So you guys have studied the Q-learning. It's a deep network because we are using the images. And the images are being processed. So we provide so many images per second, just like you're watching, and then those images are being processed through the deep Q network, and they are making a decision in real time, left, right, whatever. So this is what I'm doing right now. There's a lot of work going on right now in my lab. Yeah. So there's a lot of, this is a closed loop problem. So remember I said you don't teach the system, but let the system figure it out. Use the agent figure it out rather than teaching it. Okay? So I don't have all the slides, but I think you know, there are so many different versions on this. Yeah. No, this is another one. So somebody told us, you know, can these modes work under the water? So we dipped it under the water. This is electronics. So we dipped it under the water, and we are kind of detecting stuff under the water. So the issue is some of these electronics, you're afraid, right? You put the phone down inside the water, you know, sometimes it may not work, but no problem. So one of the projects we had was, can the electronics work under the water? And that's what that demo was. This was my campus. I thought I would show you. So if anybody interested for PhD, it's a chance. Okay, so, and these are hardware. These are all hardware-oriented demonstrations, not just MATLAB simulation, you know. I can't tell you the reasons what we are doing there, but it's being used in a number of applications that so you can see in the beginning, you know, that goes under the water. You see there's a water thing, and you'll see that in the tub, we dipped that whole thing inside the tub. You see, you can see that. You try it, it won't work for you guys. Yeah. Okay. So let's see, what else? You know, there are other ones, I don't know what this is. Yeah, localization. I think the professor is not here today. He was asking all the localization stuff. Yeah, I won't show that. So anyway, guys, there are a lot more stuff I can show. Any questions here? Any questions? I don't know what else specifically you want to. Yeah, I don't know. So can you ask him to cut it? That's enough. Yeah, you can record. Stop recording it. Situation I am in. Because I'm counting days, right? You know. So what I want to say first, there's a thanks that goes to him, and also to the professor who were there, who was trying to help set it up, and NIT Roorkela, the help that they have provided, right? We'll do that in the valedictory. But what I'm saying is, but also there's a lot of effort that, and also the GAN program, which is the Ministry of Education, that provided the funding to invite people like me to come from other countries to come and basically provide that knowledge, because as I said, it's very important for you to see that wherein you saw that video that I showed you, that's a German video that was taken 2013, that's Siemens. And you see that where the technology is going, otherwise you're out. You're out. So there are a lot of things that I was saying that, so we have to thank the GAN program for helping an NIT, and the EE department to hosting us, and as I said, Professor Bera and other professor, because I told him I have a back problem, and so they helping me, and then they know I can't carry the laptop, so I got this stick, they provided the laptop, we were doing all that stuff, and they used to bring me from the guest house, it's not that far. So they were trying to bring all that stuff. We have had all these arrangements that were made, yeah. And it was not a simple thing to do. So you have to thank him as part of the NIT. If you're an NIT student, you see that how much pains the faculty go through to bring all these things to the students. Yeah. So the only thing the faculty will ask you is what? What do the faculty would ask you to do? Huh? To study, to attend these and take care of these opportunities, right? Take these opportunities, whenever it's offered, you just be present, attend, and that's all. It's free for most of you, right? Remember that. So that's what is needed. Keep that in mind, okay? And as I said, this is what is going actually, the reinforcement learning, machine learning. Even this professor today I met from Jadavpur in the guest house, he got excited, immediately said, can you give a talk he said in Jadavpur they're having a conference, 2 conferences in December. It's now conducted by IIT Indore. He said, can you give a talk? It's a big deal, machine learning. Yeah, he didn't know this. He's from production department. So it's a big deal. Yeah. Keep this in mind. So thank those 2 that are here today. You never forget. These are not easy, guys. It's not that they can go home at 5 o'clock, 5:30. Yeah. And you become like this, then you appreciate how much time they invest in you. Okay, the hope is that you guys become successful and you become in the forefront for India. You see what I'm saying? I think that is important. All right? Thank you, guys. So I think today at 2 o'clock we are going to meet for the last tutorial. Anything you want to add for the tutorial and for the exam?
Nothing more. Just to keep it in mind, I discuss, and I told you that on event triggering,
Yeah, there's a book on event triggering. I thought I'll show you. Okay, maybe I'll show you the book. Okay, because there is a little thing in there. I was thinking of showing that. But there are a lot of MATLAB code, and there are also a lot of probably hardware. So, but I'll show you the book that came out. Let me see if I can. You can hear me? Yeah. So this book is just came out, but I think he's going to give you a little code. So this is the book that came, was published last year, June. Oops. Okay, and you see those 2 are my students. Vignesh is in South Carolina, he's a faculty member in computer science, and Avimenyu Sahu is a faculty member in University of Alabama, Huntsville. So he's also a faculty. So this book came out, and this, if you buy this book, you have a bunch of MATLAB code. You see that the ones, and you can actually see very basic stuff that we show. And the chapter 1, if you look at chapter 1, that's all you need to see. And I didn't have time today, but if you go into the chapter 1, it has a comparison, very nice comparison of this is 6. There's nothing here. I think so this book has, if you look at it, there are so many chapters. So background and introduction to event triggered control. So if you look at this book, it has some math preliminaries that, like you heard, out to stability, impulse dynamic systems, vector norms, okay, and also it compares some matrices. There are a lot of stuff in there. So then stability, different forms of stability, okay, and then it talks about event triggered control systems, and it has different type of continuous time event triggered. It kind of gives you a table how to do this, and there will be some comparisons, some simulations. So this is model based. Remember, I showed you the model based for linear system, and here is the flow chart. Adaptive estimator I did a little bit, and here is the zero order hold event triggered control system. And then there is a simulation that we compare. So we compare performance of zero order hold, fixed model based. You see that these spikes are the sampled instance, and then the one that we did adaptive. You see that how many sampled instance you have? Very few sampled instance that you need, but you are able to maintain the same performance by using that. So this would reduce. So we are comparing the data traffic on the network. So this book came out in 2024, last year. So if you want to order a copy to your library, I think that's another way to do it, and they will give you the MATLAB code, just like what you got, okay? But I think he has some examples that he has that he's also looking at it, Professor Vera, okay? Anything else you want to? Yeah, 2 p.m. I guess we are going to meet.
Okay, so welcome to the assignment number 4, the tutorial 4 also. So I gave two problem. Problem 1 is related to basically the chapter, one second, the chapter of the book by professor, that is chapter 8. Okay, so this distributed joint optimal network scheduling and controller design for wireless network control system, where you have corresponding, I guess, the slide also you have followed. This is the corresponding slide to that. In the first part, there is no event triggering stuff. Okay, so the first part, basically this layer, cross layer communication and the issues related to that, it has been discussed. So theory I am not going to discuss, already it has been discussed by sir. Now you have to correlate this thing with the system, what it is provided. But if you see the book, you will find that for this particular application, same way it goes. And what I want to mean that you just focus on the algorithms, what it has been discussed, 8.1, 8.2, and that how this utility function, because all these you will find in the programming, it has been calculated. Then how the utility function is maximized, then this BI, how it has been calculated in the programming, that you will see. But one thing I want to mention you that if you see in this book you have that batch reactor problem. But the programming what I have provided, that is not the batch reactor problem. That is a system which is different from this example. So first you can study that example and see that how the things are going, and later on you can do the programming for the batch reactor also. So mainly you have to, because this thing maybe as a control engineer you are not much familiar, because here you will find that the communication related terminologies are also there. So you need to understand those terminologies and the values what it is given. Okay. So much thing I will not, I'm not telling here, just you will see that how the programming is working. You can run it and you can see that and programming in that particular folder what I have sent, it is, you will find that two folders I sent, one is 8 and 9. So you will see the chapter, and good thing is that this programming for that advanced MATLAB is not required, because this laptop I have 2018B and that one having 2024, but the programming is running with 2018 also. So there is no issue, you can run it. No advanced version is required. Like here you see you have to open the chapter 9.1, okay, and if you see the system is as it is given in the book, in the assignment sheet, that is AC, you see AC matrix and BC matrix is given. Then with the DARE the gains are calculated, this P matrix, K matrix is calculated, but before that you have to do the discretization, okay. One second. This is your 8. I have to open the 8 one. Yes. So this is the programming I am talking about. One second. You come to the second problem. I am doing the wrong thing. You come to the second problem. Second problem is related to, actually, sorry, the second problem is related to the chapter 8. There is a mistake I did. The problem 2. This is batch reactor problem. Correct. The second problem, it has been changed, means the event triggering part. So this problem 2 you now first focus. The problem 2 is related to the chapter 8, problem related to chapter 8. And you open that chapter 8 underscore 1.m, that particular file you open, and there you will find that we are dealing with a batch reactor system where AC BC matrix is defined. Then this AD and BD, the discrete version of that continuous time plant is calculated. Then the gain has been calculated, okay, and subsequently you will find that here you will, if you read the problem statement, then you can do it. You see that wireless network system, all 10 pairs to be used for this problem. And just to run it, and you see that the things what it is discussed in the class, that you can visualize it or not. Then I will come to the event triggering part also. So this is the network latency. You can remember sir has discussed about this, that how your, whenever there is a transmission, how it is coming down, okay, so, and how the delays are managed, that sir has discussed. And this is the final plot. You can say that all the regulator errors are coming to 0, okay. So that is required to be done for the problem which is discussed in the chapter. Yeah. Which one? That yeah, means the programming. Okay. Yes. Oh, here 8 and so that need to be open. Utility comparison, yes. Okay. It is to be run. No, to run this, I think the new version is required, because it having DARE command, which is not running here. What is the problem you tell? Yes. Of dimension of? Okay. Okay. Why that so? Okay, I'll see that. When I'll go there, I'll see that. So main program is running in 2018, but other that, if you want to do the comparison with utility and the cost function also, you have seen that cost function. Okay, after completion of this, I'll see that what are the problems you are facing. That if I am able to address, definitely I'll do. So then you can go for that the theory which is discussed in chapter 9, that is event sample distributed network control system. Okay, so here first of all you should know that what is event sample. I guess now little bit sir, after sir's discussion, that it is clear that what do you mean by the event sample distribution. Okay. So for this little bit I can help you, because I am also working this particular area, event triggered control. So bit I can help you with some small example, then you can slowly you can extend that idea for this particular example also. So just to show you one example is simulated, very simple system I have taken. I am starting with continuous plant, then I will switch to the discrete one also. Okay, so you see that continuous plant I have taken, that is x dot equal to ut. It is a scalar plant. Okay, so now my objective is to stabilize this plant, to find out a u such that I can stabilize this plant. Okay, so the simplest control will be ut equal to minus xt. I can choose the state feedback, that is minus xt. So what is the solution of this system? For any initial condition it will converge, because it will be e to the power minus t into x0. Okay, which can be shown with a simple Lyapunov function also, that if you take a Lyapunov function half x square, then if you take the derivative of it, ultimately you can show it v dot will be equal to minus 2v, which is the condition of exponential stability. Okay, so now when you will, so this is the continuous implementation, but you see if you want to implement it in discrete or digital domain, definitely you have to take sample. How you will implement this control law in digital computer? Means discretize means na continuous plant can be also controlled by computer. Then at that time what you have to do, not necessary that plant has to be discretized. That is one way to do that, but continuous plant. But now you have the measurement x. Okay, now you can sample it. And now how you will sample? Generally in digital control, what you have studied, what is the sampling technique you have studied? So it is called periodic sampling. Means you will decide that based on certain issues, you will decide that okay, I will sample my signal, that is xt, suppose 0.1 second you have fixed. So then once you will fix that the sampling is 0.1 second, your subsequent samplings are known to you, because next sampling will be when 0.1, 0.2, like that, you know. That is the periodic sampling. Means you know once your sampling is fixed, you know what is the consecutive sampling instances are. Okay, so now in contrast to that, what we can do, we can do the event based sampling. We will not do the sampling at periodic interval. Instead of that, the decision when to sample and when not to sample, it will be decided by a triggering law. Triggering law will tell you, you now sample. Okay, and other time it is not going to sample. And in that way, what will happen? What is the advantage if you go for the event based sampling? Sir has already mentioned. What is the advantage of event based sampling compared to the time triggered or periodic sampling? Less computation, as well as the less number of samples you are going to pass through the network. Okay, so then essentially the congestion will be lesser, bandwidth requirement will be lesser. That is the motivation to use the event triggered sampling. Okay, so now event triggered sampling, you do not know really that what could be the next sampling instant, like your periodic sampling. Periodic sampling, if you fix that 1 second interval you will take, then 1 second, 2 second, 3 second you will take. But here really you don't know that when you are going to take the next sampling. Okay, so then how we will decide that when to sample, when not to sample? How we will decide? What is the way? By some condition. What condition? But how you will derive that condition? Okay, so for that, you see what we are doing for the event based strategy. What we are doing, we are telling that this sir has also shown this measurement error ET we are defining, which is the difference between xt minus x of tk. Okay, xt is what? The current state of the system minus the last measured state. That is the error we are defining. Okay, now you see, now the control law, instead of x of t, we are writing ut equal to minus x of tk. Okay, then what is your x dot will be? A closed loop system, if you apply this control, then it will be your system was what? System was x dot equal to minus ut, and then you have taken that control will be minus of x of tk. So then you are writing x dot t equal to minus of x of tk. So which can be also written xt minus of xt I can write. So now you see x dot t, which is a closed loop system, which is equal to minus xt plus error. Now you see this error term is not there, then it is very easy to say about stability. For all initial condition it will be stable, but now you have a error. Why that error has come? Because you are not doing the sampling at regular interval of time. Due to that, one error is going to be generated, and which is going to evolve with respect to time. Now, how can you determine the stability of the system, or how can you guarantee that the system will be stable? Now for that, again you will take the help of Lyapunov, and you will see that what condition you can impose on error such that you can guarantee the stability of the closed loop system. So then same Lyapunov function we have taken v equal to half x square, and then we are finding that v dot x is coming minus x square plus x of e. You see this additional term is there. If it is not there, then it is very easy to decide about the stability, because minus x square, it is positive definite, so it will be negative definite definitely. Okay, so now this can be written with the help of mod, because it is a scalar case, that which can be written less than equal to minus x square plus mod of xt plus mod of et. And now we are saying that et mod of et is less than k into xt. K is a design parameter. Okay, and now if we will substitute that condition, now you see that v dot x can be said negative definite only when if you say that 1 minus k square is greater than 0. And this condition, norm of or mod of et less than k of xt, can be used as a stabilizing condition, or it is the triggering condition. Means whenever the error is going to cross this threshold, it is a state dependent, basically the law, and whenever the error is going to cross this limit, then you do the sampling and the error will come to 0. Okay, then you allow the error to grow. Then error is growing over the time, and whenever you are crossing the threshold, then again you take the new measurement and then you come. So like that, the event, then what will happen? You can delay the sampling. Whenever is required, you are doing the sampling. Whenever means what? Whenever you are finding that it is violating the stability condition, then only you are triggering. Otherwise, you are sending the old measurement. Old measurement. Yes. So then only you can send the new data and you can update the control. Okay, something like that. And you see it has been plotted for this particular small example. You can also try this one, that you see that dotted one is a continuous one, and for two values of k we have plotted 0.8 and 0.2. Okay, the control law is this, and this figure is D figure is very interesting, because you see for red one, this is a cumulative triggering. Means how many number of triggering you are doing to stabilize the system. In case of you are finding that for the red curve, it is almost 30 number of triggering are there within the 5-second time of interval. But in case of the blue one, you are finding it is around 11 number of triggerings are required. So it means that, or also you see, we are not compromising the performance also. Almost similar performance between red and green, and also if you compare with the continuous time, it is almost similar. So, but what is the advantage? Advantage, you are finding that the number of samples are lesser. Okay, so same idea can be extended for the discrete time also, and that now I'm showing you. Now you can correlate what is that particular one. You see, sir has shown this particular slide for the zero order hold scheme. Okay, so here you see we have taken a discrete time system, and now we have a sensor, and we are defining the error, that is xk minus xi. So this is the measurement error we are talking about. Okay, and now we have to find out a stabilizing condition, which will be my triggering law, and if it is violates, then it is going to be triggered. So you see, subsequently we found out that condition. You will find that the condition is this. You see, this is the condition, and it is in terms of error only. So so this is a stabilizing condition you have to, and how you can ask that how it can be found out. The same, using the stability condition only. So all event triggering cases you will find that like that, and you will find that sir was talking about another called model based. Okay, so you can do that kind of triggering from this paper also. This is the paper in sir's book also it is cited, that is model based event triggered control with time varying network delays, by this particular paper in CDC, you see in 2011 paper. So here they showed that if you have a system x dot equal to ax plus bu, and you have a model of the system, then you are comparing between the ideal model and the system, and whenever you are not happy with the performance, then you trigger. So you have to define a condition that okay, my error must grow that much of level. Okay, so now that's why if we come to the, so here similar way, you see the way I have discussed, I have shown that they are finding the system in terms of that error. Okay, and once this error has found out, and then they are trying to find out a condition on error which is the stabilizing condition or the event triggering condition, and if it is violated, then you will do the triggering. And if you come to the MATLAB programming, the MATLAB programming is we will take the system given by them only. This is the system we are talking about, A and B matrix. This is given in your assignment. Okay, so now for this system, the three strategies you can implement. Actually, the programming what I have sent, that is folder 9, in that you will find that three strategies are there. You have to extract that one and you can compare. Okay, so I have actually done that extraction. You will do that one like the beginning what we did. You will split for time triggering is there, then you have that particular ZOH based triggering, then you have model based triggering, then you have adaptive model based triggering. So these are the three strategies, in fact four strategies you can see and you can compare. Like here the first programming, if you see, it is for the time trigger. Here you see, here we have taken a sampling time 0.1, then we have a continuous time system, okay, and then we are defining the Q and R, the performance indices, and then from DRE command we are calculating what should be the gain and what is the P matrix, and this is the initial condition we are defining, and then this is the loop where we are calculating the state as well as the control. Okay, here no event triggering is there. Simply u equal to minus k into x of tk we are applying. No event triggering, nothing. Simple control that u equal to minus. So now if you run it, then you can see that the system is giving the response like this. This is the control and this is the two states are converging. Okay. Now next you can go with other programming, that is the event triggered one. You see now event triggering one I am opening. Same system. Now we will apply the event triggering scheme, which is a Z08 scheme I am talking about. Okay. So now the same system we have taken, and then we are discretizing the system. Then the Q and R, everything has been defined, but now you will find that little bit changes are there. Where the change? I am telling. You see, now here we are defining that stabilizing condition. This is the, you will in this, yes, that slide you will find that one stabilizing condition is there, that we are evaluating. Okay. And based on that we are applying the control. You will find that here there is a strategy to apply the control. What it is telling, this is the way you will apply control. uk equal to k into xk when event is initiated, and uk equal to k into xy when event is not initiated. Okay. And what is the meaning of this event is initiated and event is not initiated? That depends on the error. Error, when it is 0, then event is initiated because x of tk minus x of tk, so that is 0. But here you see when x of k minus x of I, then event is not, means error exists. A finite amount of error exists, so then event is not initiated. You will check this condition, and then based on that you will apply the control to the system. And then you will find that if you run that particular, I will close this to program, and now based on this, if you rest of the things are only to store and computation, that error, control, state, these other things are there, you can do that one. And if you run it, now you see now new features. Now first thing that are you finding much difference between the stabilization performance once you have seen before with time triggered? No. You see almost similar performance you are getting. And this is the control effort. This is the control effort. Okay. And most interesting thing is that a new thing here, you will be able to see that evolution of that norm of error. Okay. What is the meaning of this? You see, you are allowing the error to grow, and this is a threshold. Okay, whenever it is going to touch that threshold, then error is coming 0. Why? Because at that time you are updating control. How you are updating? By sending the new information, current information of the state to the system. So then when you are applying the control with the new information, definitely the error is going to be 0. So in this way, eventually you are finding that error is tending to 0 and your system is stabilized and you are getting the control. But here another thing is not plotted. You can try that one, that the inter-event execution time, that is the difference between ti minus 1 minus ti, this difference. Then you can see that it is not in a periodic manner, it is more sparser than periodic. Means with less number of samples you can stabilize the system. So this is the whole theory behind it, and lot of paper, as sir said, you will find a lot of research till now. Many system, you will find that situations people are using, because all are now talking about CPS, network control system, IoT, where these issues will be there, that the transmission of packets and transmission of information through a common channel, okay, which will be constant by bandwidth, which will be constant by packet loss, everything. Okay, so if you want to minimize the adverse effect of network control system, then definitely one of the way you can solve with the event trigger. So that's why this particular chapter is dedicated that event sample distributed network control system. So I hope that rest of the thing you can do, because main part that is event triggering, and then the theory which we have learned in this particular course, it is clubbed with this, and then you can test the same thing, that effect of that here the optimal control that you can have with this. Okay. And if you able to get the 24 book written by Sir and what is the name, Abhimanyu. So then you can see at the beginning these things, 3 strategies are discussed. That is with ZOH based, model based, and adaptive model. At least if you learn these 3 things, your many things will be clear. You can go for any other application with event triggering case also. Okay. So you can see the main this is a chapter 9.1. Okay. So you can basically you can extract the you see, I was not knowing that this is there. How I come to know? By looking only. I'm not getting time to see the programming. Yesterday night only I saw this program and I found that okay, this way the things are, and all the, when you are reading something, most interesting thing is that everything you should look. You see, it is written at the beginning, example from Gracia and Antacyclis. Okay, so then I saw that okay, let me see this paper first. Then I downloaded that paper night only. What time I send you the programming? It is around 12 o'clock. So I was actually lying down and looking the programming. So that is the thing you have to also do. That you have to see the things, you have to play with the things, then only the things will come to your mind. Otherwise, no one can push you or feed you. Okay. So then I saw this paper and I saw that okay, this is the theory, it is written here. I am working in this field, I know little bit of this, true, but really I have not read this paper before, because I am not using model based triggering. So then I go through that and I understood, okay, this is the philosophy, and it is written very nicely in Sir's book, very compact way with the steps. And if you see the pattern of Sir's book, what pattern, have you seen what is the pattern? Can you see? Can you tell Sir's book, how the book is written? And also with Sir's supervisor, F.L. Lewis, any book if you see, the series of book written by Sir's supervisor and Sir's, what is the similarity you are finding? You will find that after discussing every algorithm, he will give a table. In table, you will find that what is your system, what is the control law, what is the other necessary things. So you will find that 4 or 5 steps it will be written, that if you use for programming, it will be great help. It is summarized. No need to really look into the details of that. Details definitely you have to see, but programming I am telling, you can do that one. So this is the way you can play with that. Also you will see that cost function comparison, fairness comparison, all these comparisons are there. So you can do that one. But to understand this little bit of communication stuff also you should know, because we do not have that much of strong background of communication, but at least if you see with the fundamental background, you can understand that one. So I hope that that's all from my side. Now little bit I will roam around to see what the problem you are telling to me. And you see only, you see, This is the comparison for three algorithms, that is proposed distributed scheduling, then embedded round and robin, and greedy scheduling. These are the three algorithms they are basically, and fairness comparison also you can do. I think this will. Okay, so then you play with the code. So I will stop here, and then in between you need any discussion, we will do that one. Okay, so I'm stopping here.